Sm0.60Sr0.40MnO3. Good evening. Today we'll try to do summary to this article. This article's title, intrinsic electroresistance of these two different components, the same components, but the different are the concentrations to these two elements, here 0.6, but here 0.55 and 0.4, 0.45. The same elements, the same compounds, but their concentration are different. We will use some diagrams, some image to explain to us what these differences mean, what the important things. We will focus on some areas, some decreasing, increasing, and we will try to understand what all of these meanings. Now, the outline will be abstract introduction. Actually, at abstract and introduction, I will take simple ideas, simple information, and go on going deeply at experimental details about the other important information about the diagram and all things like that. Here at the first slide about abstract, the author focused on two components, like I said before at the first slide. Here, the same components, the same structures, but with different concentrations about these two first concentrations. All of these components made from the same way. Here, we are using not continuous current, but pulse current. It's different, maybe 2 milliseconds, microsecond, and drastically decreasing the contribution of Joule heating on the electric resistance. We will focus on Joule heating because and sometime will work and sometime will be useless. And I will explain all of that at the next slides. We find the change of the intrinsic carrier concentration to these two components with these two different concentrations. Now, the parent shape to these two components is R1X, AX manganese, 3 atoms of oxygen. Air, R is the rare earth, like we know. A is the alkaline earth. To all of these two structures with different concentrations. The manganites of the structure, SMO, we can say, are examples of system where multi-phase competition plays a prominent important role. Important the same. Recently, interesting electroresistance results, which show at the next slide. We will focus on important information. The resistance will be equal a huge ratio, equal what, why. We'll discuss all of this information at the next slides. Here, the isolating material transition to X equal 4.4 will equal 120 Kelvin, and when equal X equal 0.45 will equal 123. That's mean increasing a little bit. And we will prove that by using some images. Here they observe dramatic change, and we're dealing with some change field. The first one is the resistance but specifically at high current, and decreasing the isolating material temperature dramatically. And the third one, the hysteresis upon between these two different periods, cooling, warming, and warming, cooling. They concluded that the results can be explained primarily by Joule heating. Like I said before, we will use Joule heating in some place, specifically at the age when the increasing or decreasing, while the decreasing and increasing. until stopped, until be constant or equal 0. Here at these two different periods, the Joule heating will work. After that, at the flatness will be useless. Investigated the resistance of polycrystalline to this component using pulse current excitation, where DC was applied, but to just few micro or milliseconds. They observed a giant decreasing of the resistance in their sample. This ratio is huge because the decreasing of the resistance equal 250,000, 250, yes, 250,000, 100% at high current, much higher than previous work on the electric resistance. That's meaning we're dealing with a huge decreasing in the resistance, approximately equal 2,500, 100%. But at the condition at just high current. Here, like I said before, we will focus on these two concentrations, 0.4 and 0.45. Samples were prepared using the same solid state reaction method. To make all of them, they use the same solid state reaction method. Here, some information about the atoms, the components, the content to the structure, let me say that, of Sm2O3 and SrCO3 made at a high temperature, approximately 1,375 at 24 hours. That's mean at a day. The resulting samples were pulverized, pressed into bottles, and the temperature will increase a little bit to be 1,473, but at the same time to 1 day. A second centering at 1,473 Kelvin for 24 hours was carried out. At the last, will be at the same temperature, but double time to be 2 days. To prepare all of these three parameters, to prepare all of these three contents. The resistance of the sample was measured using what? Using the 4-probe method with silver contacts that are supposed using magnetron source into the sample, the 4-probe method. This is important with silver contact. And now we will use two different tools. The first one is the nano voltmeter Y to can determine the mini voltage, the smaller amount of voltage on this axis, useful for measuring the small voltage drops, where Joule heating is also very minimal. And the second tool is oscilloscope, was used to measure the voltage, but at high current excitation, specifically at high current excitation. Here, experimental details. The important slide started from here. Here we have two slides. First one when x equal 0.4, here equal 0.45, with different amounts of current. At the same time, the diagram will be from x-axis, the time at microsecond, not milli, microsecond, and from y-axis will be the volt at volt unit. At first, at 1 milliampere, we will start from zeros. 0 will be the start point, approximately 0, near from 0. This point, near from 0, will be the start point to all of these different amount of current applied from here until 200 milliseconds, we will note simple decrease to come back approximately near the start point. And when start to increase the current, 5 milliampere, 10, 30, 50, we will note at first the voltage will decrease, will increase. For example, here at blue one, it's approximately 5 volts. But here at the last one, approximately equal 40 volts. Because that's mean when increase the current, the voltage is increased too. And after that, here at this flatness shape, the results will start, will be constant. For example, here at, let's say, at 50 milliseconds. After 50 milliseconds, the result will start to be something like constant until 200, and after that, the voltage will decrease again. Here, this flatness, the Joule heating is useless, but the Joule heating method, it's useful at specific the edges from these two sides. From here, this increasing, we can use Joule heating. And here at the decreasing started, we can use Joule heating. At the same time, at here, we have another diagram, but not from 0 volt until 40 volt, but here from 0 to 1. 1 microampere is the first one from here, and after that be something like approximately constant, and after that decreasing suddenly like that. And all the other colors act the same behavior. Here at x equal 45, from black to green to blue, the same situation will increase and be constant, but here less than 50, maybe 37. After 37 will be like constant at this flatness area, and after that decreasing like that. When increasing the current, the voltage will increase, but here some difference. Here from 0 to 30, here from 0 to 40, and the milliseconds individuals the same until 500 microsecond. And here from 0 to 1 volt, approximately increasing suddenly, exponential increasing, and after that be something like constant and decreasing. Here we note some hysteresis behavior. It's decreasing early than the others. All of these at after 200 microseconds. Here, lower current below to x equal 40. Like I said, I explained all the important information about these two images. Here at flatness, this flatness, like I said before, indicates that Joule heating is not important here. And this situation, the average voltage of the plateau, that means all of this area, it's smaller than mountain, because that we say plateau. Plateau like is equivalent to the intrinsic voltage drop across the sample. However, at high current, there is a clear decreasing of the voltage. At the second part I'm talking here, increasing, huge decreasing about the voltage. Let me take a look. Yes, decreasing the voltage of the plateau-like region, implying that Joule heating is playing progressively more prominent role. Like I said before, the Joule heating will work at the edge and at the two areas, decreasing and increasing, but at the flatness will be useless. The internal temperature of the sample is rising. Obtain a responsible estimate of the intrinsic electric resistance for each current plus. We use the average of two values. Here is important. The first one of these values is the average of the voltage, within the pulse away from the rise and decay edge. Which one is the rise? Which one is the decay edge? The rise from these two sides until the decreasing the age or disappear the age or go until a little amount. Here, these values is the average of the voltage within the pulse away from the rise and decay age. If there is significant Joule heating, which cases decreases in the voltage in the plateau-like region, then this value underestimate the intrinsic voltage. Here, underestimate is important. The second one, these values is the extrapolation of the voltage. Extrapolation of the voltage here is important. What that mean? That mean we will take another look, but from back to start point. And after that, we will note the hysteresis phenomena about this component. And I will use another image to explain this hysteresis phenomena to us by clear way. We depend on two things. The first one, the values of the average voltage within pulse away from rise and decay the edge. The second one, the extrapolation of the voltage from back to start. Here, let me explain the extrapolation from back to start point. That's mean from back to start point, from at x equal 4 and at x equal 0.45, back to start point. But here, like we know, here it's not the start point. Here it's more than 50, but here it's less than 50. Here, the maximum point at the flatness equal, we can say 3.9, something like that, approximately 3.9, less than 40. Here, approximately 37. Okay, but here, some different about the behavior. It's not flatness like that. The start point is different and didn't reach this values about the less than 40, less than 30. Here, the situation is different. Here, the component acts hysteresis behavior at all of these two different compounds of X. The intrinsic voltage, since Joule heating, should only become significant during part of a rising edge of the current pulse. Hence, this second value should be viewed as an upper limit of the intrinsic voltage, The difference between the two values provide an estimate the error. Here the error is clear, some difference between the first and the second image from start to end, and from end to start, back to start point. The shape acts another behavior, because that we say hysteresis behavior didn't take the same copy, the same image, didn't plot the same image. The difference between the two values provide estimate of the error, like I said before, and our estimate of the intrinsic voltage or resistance. Furthermore, at low applied current, here Joule heating is not an issue. It's not important. The nano voltage, like I said before, we used it to calculate, to determine the volt, the minimum, the small amounts of voltage. Here, it's important note, there is no change in the average voltage with the width of the current extension pulse about these two situations. Now we will talk about another figure. Here, show the temperature dependence of the intrinsic and resistivity. Some strong relation between the temperature resistivity and temperature resistance. Estimated as described above using 200 microsecond pulse to x equal 0.4, x point equal 0.45, respectively, while warming from base temperature. Here, each the temperature and current data point in figure was obtained from the offline analysis. Here is the important image is here. Here we have at the x-axis the temperature at Kelvin, and from y-axis the resistivity at ohms centimeter. Okay, and we have a different amount of the current, start from 0.1 milliampere until 50 milliampere, and we will say what will happen and what all of these colors mean. We also see similar behavior if we use DC current extension, but here we use pulse current. By contrast, as seen in figure 3a, the Joule heating contribution is minimized. There are much smaller reduction of the resistivity. Let me explain that. At 0.1 milliampere, start approximately equals 0, and after 75 or less than 100, this curve start to be able to increasing to the maximum point. Here we have interesting thing, all of these curves, all of these different amount of currents share the same isolating material transition temperature. Let's keep going. Like I said before, pulse with 200 microsecond. Okay. The first one, 1 milliampere. The red one, 10 milliampere, 20, 30, until 50. All of these share the same isolating transition material, transition temperature, sorry, equal here, approximately 127 Kelvin. What does mean? That means at 0.1 is the first one, and at the maximum amount of current will be the smaller one. What does mean? That means at increasing the current, the resistivity will decrease. By this curve, we prove. By using this curve, we prove at increasing the current, the resistivity is decreased. But all of these different amount of current equal the same 127 Kelvin at X equal 0.4. Now let's take a look to the other. Here when X equal 0.45, all of these different amount of current equal the same isolating transition temperature, equal 137 approximately Kelvin. Here, the same behavior, but with huge difference. Let me explain how. Here at 0.1 milliampere, the maximum resistance, when increasing it, the resistance start to decrease, but little bit smaller than when X was equal 0.4. We have decreasing, but it's very, very small comparing with the last image. Here, I take all of them together. Here, 127. Here, 137, approximately Kelvin. The different amount of current are the both of them, but here start from 1.01 until 50 here from 0.1, but ignore the 10 and 20, but the same until 50 milliampere. Here the decreasing is clearer than this image. Here the resistivity decreasing, but little bit smaller than the first situation. And the isolating material transition temperature didn't shift to another result, will be at the same to all of these different amount of currents. Here, the last image will explain to us the relation between the current density, not current density at x-axis and the resistance at y-axis, and explain to us the resistivity behavior to all of these x.4 or x equal 0.45. At x.4, the decreasing of the resistivity of the resistance is clear, starts from 1 until approximately 0.7 at less than 5 current density. But here, sure, we have two decreasing in the resistance, but the situation is different. Start from 1 and at approximately 0.95. It's less than from approximately 0.7. Here clearly shows that the isolating material temperature of the sample, the intrinsic change of the resistance with current density and also current are significantly peer the intrinsic resistance and IM temperature to the structure when X equal 0.4 is bigger than, like I explained here, it's clearer than and bigger than the resistance, the decreasing resistance at the X equal 0.45. Here, the summary on the last slide, we have investigated, was working on two same compounds made from the same way, but with different construction. Like I used the blue color, here 0.4, here 0.45. The electronic resistance depend on the magnetic of the current and the large change between these two different compounds, the different concentration. The explanation about what the reason of the heterothesis behavior is, we attribute this difference about the hysteresis behavior because the contrasting homogeneity of these two components. I repeated it again because contrasting homogeneity of these two components. The estimates of the electric resistance are dramatically smaller than those previously measured in the same composition by others. At the last, it's useful work to understanding electronic resistivity materials for applications. Thank you about your watching, your listening. Have a good day, and I wish it was helpful.